conservation of mechanical energy with only gravity and or spring affecting the motion. So look, if you have a situation, where the only force affecting the motion of the object is gravity and or a spring, then what you can say is this. You can say mechanical energy initial equals mechanical energy final, right? And what do we mean by mechanical energy? Let's be super clear about this. Mechanical energy is what? There's three forms of mechanical energy. We have kinetic energy, we have potential energy of gravity, and we have potential energy of a spring. And the equations are, you don't have to memorize them, I'll give you the equations. It's 1/2 mv squared for kinetic, mgh for potential of gravity, and then 1/2 kx squared for a spring. K is the spring constant. All springs have their own spring constant. And then x is how far the spring was stretched or compressed. So if there's only gravity or spring present, gravity or spring affecting the motion of the object, then this will be true. Okay, so here's the situation. We have a skier. That's why we watched the video of Tommy skiing. We have a skier going down the hill, starting with a velocity of 2 meters per second. Now, for this example, we're going to say that the hill has no friction. Because if friction were present, would that affect the motion? Yeah. And is friction a force other than gravity or spring? Yep. So we got to talk about that in a minute. So for now, we're going to say no friction. So here's what I want you to do. Use conservation of mechanical energy to figure out the velocity of this guy. So this guy goes down, 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 right? Down the hill like this. When he reaches the bottom, when he's down here, so here he is, what will be V final at the bottom of the hill if there's no friction? All right, so I'll give you one. You should be able to do this in like 90 seconds. So take 90 seconds. Pause the video here. Okay, so conservation, mechanical energy. So basically what we're saying is this. Well, first let's set our 0 point. 0 point is important for this, for H, where you measure H off the 0 point. Where would be the best place to put the 0 point for this problem? The bottom of the hill, down here. This is the 0 point. Down here is H equals 0. Okay, so mechanical initial equals mechanical final. So basically we're saying kinetic initial plus potential of gravity initial plus potential of spring initial equals kinetic final plus potential of gravity final plus potential of spring final. Does this problem have any springs? Nope. So the spring ones cross the spring out. There's no spring energy. They're gone. Okay. So up here is the initial. Here's the initial. Here's the final. So looking at the guy at the start up here, do we start with kinetic? Is he moving? Yeah, he's got a velocity. So don't cross out the kinetic. Does he have potential of gravity? Yeah, because he's above the 0 point. Gravity can make him go faster, right? So don't cross out potential of gravity. If you're above the 0 point, then you have potential energy. All right, final. So now look down here. Does the guy have kinetic? Yep, because he's moving. Does he have potential of gravity? No, because he's where? He's on the 0 point where H is 0. So what we're left with kinetic initial plus potential of gravity initial equal to kinetic final. Right? So now you plug in your equations. You go 1/2 mv initial squared plus mgh h equals 1/2 mv final squared. So notice that every part of the equation has m. So what can you do? You can cancel the m's. The m's cancel out. Now what I would do, I'd kill the 1/2s. How do you kill the 1/2s? Multiply everything by 2. And then we're solving for V final. So rearranging this for V final, velocity final, which is what we're looking for, is going to end up being the square root of V initial squared plus 2GH, right? So now we can plug numbers into this. Here, make some room. So when you plug the numbers in, V final, we're going to go, so V initial was 2 plus 2, so gravity is 9.8. Don't make gravity for these don't make gravity negative for these energy problems. And then H is always the vertical height, which was 30 meters. So V final answer comes out to be 24.3 meter per second. Okay? That's the velocity of the skier at the bottom of the hill. Now, here's what we got to talk about. So any questions on this? Because we're going to take it one step further. Yo.
I'm kind of confused. Like, does the angle of the slope make a difference?
Good question. So this theta right here, that does not make a difference. It would make a difference if friction were present, because friction depends on normal force. But for a situation where there's no friction, all that matters is the vertical height. That's all. That's it. Thank you.
You're welcome.
Tristan. Okay, so did you have a question?
Why is it square rooted?
Oh, because velocity final is squared.
Oh,
So,
okay.
so I had to square root both sides. Mm-hmm. All right. Now, let's look at this situation. Okay, so here's a very similar... Oh, wait, what the hell? Conservation. Oh, man. I didn't save it. Oh, well. Okay, we're going to keep going. All right, so very similar situation. We got the guy on the hill, but now friction is going to be present. Friction is present. What? Oh, no, don't go down. Okay, he starts with an initial velocity of 2. Sorry, guys. I had this all set up. It's the same situation, but now there's friction on the hill. I think I forgot to click save. Okay, so he starts with a velocity of 2. The height of the hill is 30. When he reaches the bottom of the hill, he has a velocity of 5 meter per second. Okay. The question is, find the work done by friction. Find the work done by friction. Okay, look. Do we have a force other than gravity or spring affecting the motion of the skier? Yes. And what's that force? Friction. So we have to account for it. So how do you account for it? Well, you go like this. You go mechanical energy initial plus or minus the work that was done equals mechanical energy final, right? Because what did we have before? A second ago on the previous screen, what we had before was mechanical energy initial equals mechanical energy final. But look, in this situation, this will not be true. Why will that not be true? Because of friction. Now, is friction going to add energy to the skier or remove energy? It's going to remove energy, okay? So, is this going to be plus or minus here? It's got to be minus because friction's going to steal some of the initial mechanical energy. So this will be minus work of friction. So what I want you guys to figure out is the work. I want you to solve for this. What is the work that friction did? Look, I forgot. Hey, guys, I had this all set up perfectly, and then I forgot to save it. You need the mass for this for this problem. So the mass of the skier, we'll say, is 35 kilograms. That's important for this question because if friction's present, then mass is going to matter. Okay, mass is not going to cancel out. All right, so how do you solve for the? So we're looking for the work that's done by friction. The skier starts with 2 meters per second, goes down the hill at the bottom. He's going 5 meters per second. The vertical drop is 30 meters. Hey, when it was no friction, we just did that. When it was no friction, what was his velocity down here? 24.3, right? That would be his velocity if there was no friction. But there is friction, so he reaches the bottom going 5 meters per second. So what's the work done by friction? Well, look, at the top of the hill, watch. So at the top of the hill, he has mechanical energy initial. Now remember, there's 3 types of mechanical energy. Put 1, 2, 3. Mechanical energy initial. Does he start with kinetic at the top of the hill? Is he moving? Yes, so he has kinetic. His initial kinetic is 70 joules. How did I get that? 1/2 mv squared. So I'll let you calculate that. 1/2, his mass is 35, his velocity is 4. Punch it into your calculator, you should get 70. Okay, does he start with potential of gravity? Yet with the 0 point being down here. Here's the 0 point, down there. Does he start with potential of gravity? Yeah, because he's above the 0 point. mgh, you plug that into your calculator, you're going to get 10,290 joules. All right, the third form of mechanical energy is potential energy of spring. Is there any spring up there? Nope, so that's 0, right? What is his total mechanical energy initial? 10,360 joules. How did I get that? I added these two together, right? His total mechanical energy initial, 10,360. Now, come down here to final. Mechanical energy final. Let's list them all. 1. Does he have kinetic at the bottom of the hill? Is he moving? Yes. His kinetic energy at the bottom of the hill comes out to be 438. I think I actually rounded that. I think it's 437.5. We'll just call it 438. Okay? How did I get 438? 1/2 mv squared. His mass is 35. His velocity is 5. Punch it into your calculator. Does he have potential of gravity? No, because why not? He's on the 0 point. Does he have potential of spring? No. So what is his total final mechanical energy? 438. Ba-bam. If this were money, you'd be pissed. You'd be mad. At the top of the hill, if you started with $10,000 in your pocket, and then at the bottom you had $400, you'd be like, what happened to all my money? Right?
Wall Street.
Huh?
It's called Wall Street.
Yeah, Wall Street happened. What stole, so see here, there's a difference between these. What accounts for the difference between these? Friction. So look, mechanical energy initial was 10,360. Mechanical energy final, 438. So how much work did friction do? It's got to be what? 9,922. Do you guys get this? The answer is the work done by friction is 9,922 joules. It's the mechanical energy lost. Yo. Sure. Did this help? Okay. Now let's go to the worksheet.